you're exposed. So if you double the amount of time that you're holding it, you're going to double your dose. I mean, that's just the direct thing there. The inverse square law, though, on the other hand, is a little bit more involved. And again, if you take a look at your math book on page 89, okay, we have some problems that I could guarantee you will definitely see on your board exams. They always have inverse square law on here. Okay, so traditionally, this is the way that they normally write it. They have the initial distance that you measure, the initial intensity, and usually this can be an MR or counts or things like that. To give you an idea of what they mean by inverse square law, okay, if we have a direct relationship, I1 would equal D1, that would be a direct relationship, correct? Mm-hmm. Okay. With the inverse square law, the initial intensity of the radiation, which they'll give you an MR per hour or something like that, you're going to have that over the new intensity or the new measurement, and then you're going to have it set up as the second distance squared over the first distance squared. I don't know if you've ever done these kind of equations before, but typically you get something like this. Okay, you have a source of radiation. Now this formula only works for point sources. Okay, does that make? A point source is a very small emission source.
So not saying that's...
Yeah, well, I mean, if you stand further away, your radiation dose is lower, but it's not going to follow the inverse square law. Because once you inject the patient, then you no longer have a point source. Well, it's in the syringe. You know, typically that's why they said that if you could take like a half a cc and put it in a 3 ml syringe, that's still equivalent to a point source. But anything larger than that, you don't get the same geometric distribution. So typically it works something like this. If you have a source of radiation, and let's say you were exposing something at 1 centimeter away, okay, we'd be just exposing, let's say that the square measures 1 centimeter. Okay, so it's a 1 centimeter square. And let's say that that's at a distance of 1 foot. If we double the distance, by nature radiation is divergent, which means that it kind of travels out away. And by the time it gets to, let's say, 2 feet away, now you're exposing 4 times the area. So you would have 4 1 centimeter squares. So if the distance here measured 10 MR at 1 centimeter, at 2 centimeters, that same radiation intensity is being now distributed over 4 times the area. So now each one of these little squares is equal to 2.5 MR. So that's how the radiation dose would be reduced. It's not that it's actually less, it's just that it's less over a given area. That sort of makes sense? People remember from X-ray days? Yeah. Okay.
Too long.
Well, the thing that you're going to be seeing, or I'm trying to think of some of the math problems that were in that. There's some that are in that book, but here, this is a good example here. A technologist is exposed to a dose rate of 80 MR per hour, standing 2 feet from a radioactive source. What will the dose rate be at 3? Okay, so if you were going to solve that problem, let's take a look at that one there first. Okay, the 80 MR and the 2 feet, this is your first intensity, and that's your first distance. Where most people have a problem is that they forget to square the distance. And I told you before we had a relationship of I1 over I2 is equal to D2 squared over D1 squared. Anytime you have a proportion like that, you cross multiply, right?
Mm-hmm.
Okay, so what the easier way to do this is to put this as I1 D1 squared is equal to I2 D2 squared. To me, I don't know why people bother to set it up like that. It's just, you know, sometimes they have old distance, new distance, or new intensity, old intensity. It doesn't make any sense. But in our example here, okay, so the intensity is the 80 mR per hour. The distance is 2 feet, so that's going to be 2 feet squared. And then what will the intensity be at 3 feet? So there's your x. And then you got 3 feet.
So that's 9x
Yeah, so you've got 9x on one side,
equal to
320.
320, yep.
Okay, so 9 into 320 is going to be roughly
25.
yeah, 9 into 30.
35.55.
You got a good calculator there. Okay, so that's what the intensity is going to be. And that's a typical question, or that would be something that I would give you also. You know, radiation source measures this amount. You know, what would it be at this distance? The other type of question that you would get is, at what distance would this be equal to 2 mR per hour? So let's say that we had a problem here. Like,
0.55.
yeah, let's take a look at number 5. Right at 20 mR per hour, 1 foot, how far away must you be for 2 mR? Okay, so the same thing.
10.
I1. Okay, so you have 20 mR, and you've got 1 foot squared, and that's equal to 2 mR and x squared. And again, you got to remember the x squared. Okay, so basically you can divide both sides by 2, or you have 20 mR equals 2x squared. Okay, so basically divide both sides by 2, you have 10 mR equals x squared, and then you'd have to take the square root of both of those to find out what x is, so about 3.3 feet. Is that what you get? But again, the main thing is to remember for any time you're using distances, you're going to be doing squares, so roughly about 3.3 feet. Anytime you have a proportion, though, remember that both sides have to equal each other. That's the important thing. Okay. Some of the other things are, let's see here. This is where you will probably see most of the types of questions on your board exams. Whenever in the math book they have additional applications, that's a good question. So it says NRC 10F. Remember, we already learned what this is now. This is the Bible of that. What's TEDE stand for? Okay, total effective dose equivalent. This is the combination of your, what they call committed effective dose equivalent and your deep dose equivalent. Committed is your internal dose plus your external dose. Okay? We'll talk about what that means here in just a little bit. Anytime you see something like that, looks out of focus to me here. Yeah, that's good. That's good, Chris. Okay. So we'll talk a little bit about that. But you guys feel comfortable with inverse square law? If I give you some more problems with it, you know, for practice.
For homework, yeah.
I can guarantee that you will see those on your board. Okay. They always have a couple of inverse square law problems just for fun. Okay, the other thing, okay, so time, so limit the time, increase your distance. Shielding. What do you guys remember about shielding? Okay. Well, we know that, okay, first of all, we have to look at the type of radiation that we're dealing with. So alpha, beta, and gamma.
Gamma and X-ray.
Okay, yeah, so gamma and X-ray about the same thing, okay? Remember that alpha particles are stopped by a sheet of paper. Beta particles will penetrate paper, but you know, they don't penetrate too far in materials, so you know, things like plastic are good absorbers. In fact, remember, we're supposed to use plastic as our shielding or any other low atomic number. Gamma rays, on the other hand, they go through everything, and we typically need lead or some other high atomic number to stop it. And the principle behind the lead and everything like that is we have a, or you tell me, why would we select lead over these other materials to stop gamma rays and X-rays? Well, the high atomic number, why is the atomic number important? What's the relation? What did it say, Sing?
No, I said it stops the energy of the electrons. It's higher than the energy.
Okay, by what method though? What's the method that lead would stop the radiation here? Remember, we had a choice of coherent,
Is it Thomson?
photoelectric, Compton, pair production. I don't think we'll worry about triplet. And photonuclear disintegration. Okay, yeah, when you want to totally stop the energy, you need to have photoelectric. And what was the primary, I mean, besides the energy of the radiation, what was it about the material that was important? What factor in this lead would make it more efficient for stopping?
Thickness?
Okay, the atomic number. Remember, it's the Z number cubed. If you want to figure out the probability of a material stopping a radiation, it's the atomic number cubed. There's another formula that you'll see. It's Z cubed over the energy to the fourth power, something like that. What it's basically telling you, though, is that for gamma rays, it's primarily the energy of the radiation that determines how much material we need to stop it. And in fact, if you remember, a lot of times what we have to do is try to have the photon lose energy through Compton interactions first. This is where we need the number of electrons per gram. Remember that from a long time ago? So if you have a material with a lot of electrons in it, you put that in front of the high energy gamma ray, that slows it down through Compton interaction, or not slows it down, but causes it to lose energy, where then you're able to photoelectrically absorb it with a high atomic number material. It's a very typical way that they set up shielding, especially for PET or other materials like that. Okay, the other thing about shielding that you all remember is this formula here. Okay, and what did you say that was?
Lambert.
Yeah, this is the Lambert-Beer, the Beer-Lambert law. You'll definitely see this, you know, for CT it's a big thing, but anyway, if you remember how to do calculations with this is just like our radioactivity calculations, where this represents the intensity before the shielding, this is the intensity after the shielding, and then remember that it follows Euler's number. In other words, it follows base 2.718 as far as being absorbed. So, for example, and then what does this UL mean? you're close. This is called the linear attenuation coefficient. I know it was a long time ago when we talked about this. Okay. And, let's spell it wrong, but anyway. But basically, this is the percentage of photons that are removed per distance traveled. So, remember I told you that if you had a centimeter block of material and you have 100 photons over here and 60 of them come out over on the other side, then the amount that was removed is your linear attenuation coefficient. So you would have 0.4 per centimeter. Okay. And the way that this would work then is, now you could, if I put another centimeter of material in front of this, then 60 times 0.4 is 24. So 60 minus 24 would be the approximate amount of radiation that would be on the other side here. So that would be a good estimate of what it is, but that isn't what the actual value would be. Because what would it, see, if I subtract 24 from that, it's going to be 6, and so you'd have approximately 36 there. If we actually did a calculation using the formula, if I have 100 here, that's my original intensity, and then e to the minus 0.4 times 2, okay, what is x going to be? I want you to get used to practicing using that exponent on your calculator. Y'all have your calculators up there in Fresno?
Yes.
Okay, good.
Like 45.
Okay, that sounds about right. So if you convert 0.8, accessories at. You know, I hate this. God, I hate the new Windows. Okay, so on our calculator here, and this may be the calculator that you have to use on your test. That one that's on the computer? I hope not, but you never know. Okay, so we had a 0.8. Okay, we have to make it a negative 0.8 because we're losing photons. Then we have to go to the inverse over here, and we hit the natural log. Okay, so we should get 45.44. Okay,
Would you hit again?
okay, on this one here, I need to hit the inverse. Let me go back here. So we had 4 times 0.2, and we got equals 0.8. Okay, we made a negative sign on it there. Okay, now if I just hit the inverse button here, or I mean if I don't hit the inverse button here, then what I'm doing is I'm converting this number to a base 10. I'm sorry, I'm converting a log, or the Euler's number to a base 10. So if I do that, now I can work with it in a base 10 system. The problem with this formula is that we have base 10 and base 2.718 on the same line here. But anyway, so I need to hit the inverse of that, and then I hit that. This is my natural log, so we've got 45. So 100 photons. Now, why the big difference between the 36 and the 45? Okay, that was a question that used to bother me as a student. Okay, I passed my board, so I didn't care about it until I had to teach it again. So, can anyone tell me why they think that there is a difference between what we should get here versus a higher number over here? see the problem, see the dilemma? Theoretically, if I just put another centimeter, it should be about 36. But when I use this equation here, I get 45. Okay, the reason why this number is higher is because it takes into account what we call side scatter and back scatter. Okay, so you're always going to, if you just try to do it directly by just adding a centimeter and then doing the multiplication, you're not going to get the same value as if you use the Lambert-Beer formula. Because what's happening, you have, you know, we said the radiation is going like this. If it was straight linear, then that would work out. But the problem is you have some radiation that goes up here, hits something, and this is called side scatter. And you also have radiation that passes through, hits something, and comes back. So you've got back scatter. So that's why it's going to read a little bit higher when you use the Lambert-Beer formula than if you just did straight linear attenuation. So now you can sleep at night again. I know you stay awake at night worrying about this. Okay? But like I said, this is linear attenuation coefficient. As Greg pointed out, there's also a thing called density. And we all know that as the density increases, so does the ability to absorb radiation. So we do have another thing called the mass attenuation coefficient. I don't think they're going to test you on it, but I think you probably should be aware of it. The mass attenuation, we basically take the linear attenuation and we divide it by the density. Okay. Remember, the density is grams, usually per cubic centimeter. Okay. And it's the same formula, except, okay, so you have your original intensity here, you'd have E, and then to the minus, and instead of using a UL, they're going to use a UM. Okay? And then you're going to have to multiply that by the thickness and the weight. I mean, to give you an idea of how this can change, if you ever make pancakes, you ever make pancakes on the weekend? Now, I normally start out with a little tiny bowl. I put the flour in, and then I put the water in, and then it's like too runny, so I have to put in more flour, and then now it's too thick, so I've got to put in more water. Okay, so by the time I get through, I've got a bowl. I have to make like 100 pancakes. Okay, but basically, the only two ingredients I'm putting in are flour and water, right? But I can change the density of it. If I put in more flour and less water, it's denser. If I put in more water and less flour, it's less dense. And that affects the absorption. Materials in different physical states. A gas, let's say we're talking about water vapor versus liquid water versus an ice cube. It's all three different physical states of water, and they all have different linear attenuation coefficients, but if you were to calculate their mass attenuation coefficient, they would all be the same. So mass attenuation coefficient is going to show you what the attenuation value is for a particular material, regardless of its physical state. Okay? We don't use it very often. I mean, in radiology, we use it because we have different densities of barium that we make up. If I'm doing an upper GI, I have maybe a 15% weight to volume of barium. So that means 15 grams of barium dissolved in 100 ml of water. So when the patient drinks it, it's very liquid. Okay? Sometimes I need to use a really thick barium to coat the mucosa of the colon or the stomach. So I might use 115% weight to volume. So that would be 115 grams of barium dissolved in 100 ml of water. All it does is it's the same material, it's just water and barium, it's just thicker. But this is also the principle behind bone density. When you guys do bone density scans, same thing here. Bone is bone, but depending upon the density of it.